So today we have Boris Badrov. He's dev by day and also kite surfer by day. Otherwise pretending to be a chef by cooking whatever dish he found on YouTube. Next up is Boris Badrov and his indexing story.
Cool. Hello. Hello? All right, cool, coming through. All right, it's all right. Is that coming through? Yep, cool. All right, hey guys, I'm Boris. So, I'm an engineer at VGW. I've been working in the industry for roughly 4 years. And for the majority of that experience, I have known indexes as they make a database go fast, and that was the extent of my knowledge. So we had some issues with an application that I was working on, and it was, oh, okay, we're gonna use an index. So I got compelled, hey, let's figure out what this is. So today, what are we learning? We're gonna be learning about indexes, how do they work, indexing techniques, and how to debug indexes. So this will be going off Postgres' implementation of indexes, but this is relatively a high-level talk, so the concepts should translate over to other databases as well. Shout out to the sponsors today for making today possible, and also to the volunteers and the AV team of everything for keeping everything organized. All right, today we are doing some work. We are a website recipe aggregator. We get something like Reddit, Hacker News, we get recipes from other places, and we display them for everyone to see. Cool. So we're working on a product, we're working on a feature, and we're gonna be generating some reports with some queries, essentially. So we're gonna be working with one table today. It looks something like this. It's quite straightforward. If you're not sure what generated always as identity means, it just is an incrementing number that the database does automatically for you. So it's always gonna be unique. And some example data that we have here. Minutes is in, cooking times in minutes as well. And yeah, so we've got roughly around 1 million rows today. So it's not a huge table, but it's decent enough to illustrate. So we're working with a product. The first feature we want, it uses a query, something like this, which is somewhat straightforward. Let's do some testing. So dev is okay. Cool. Let's go to prod. Now let's deploy. Huh, it didn't work, right? I wonder why. Let's revert the change, let's go back, and let's talk about what did we just do? I'm gonna give you a cooking book, and I want you to keep this for the rest of the talk. So I ask you, hey, can you find me all recipes of garlic? Go through the book, we go, okay, you go through the book, you have to go through the whole book, page by page by page by page, all the way to the end, because you don't know, maybe that last page has a recipe with garlic, but you don't know, so you have to go through the entire book. So that's called a sequential scan. So we do a bit of Googling, and obviously I'm here to talk to you about indexes, so let's use an index. Let's get this over and done with. I get the syntax, Stack Overflow tells me this is correct. I will always trust them, obviously. Cool. Dev is again, fine. Let's go to prod. It's done, easy. Okay, well, what did we just do? So, again, cookbook. I give you the cookbook, and conveniently it has a thing, well, called an index, right? Which translates to databases. So go to the index, go down, you go to G, find garlic, and you find all the recipes that have garlic. And then you have the page numbers. And then you can go to the book, and you find all the recipes that have garlic. Much quicker than going through the whole book. So something like so. We have 2 recipes with garlic, chicken roast, and garlic bread on pages 800 and pages 6. So, before I explain databases, let's talk a little bit about Fairy. What is an index? Well, in this case, so there's a few different types of indexes here. Default is B-tree. And I think it's every database is default a B-tree. There's a whole bunch of others, but they're very complicated. I'm not going to cover them. So, B-tree. What does it look like? Okay, so at the top, we have the root node. At the bottom, we have the leaf nodes. And you can notice it's kind of ordered with the smallest numbers at the left, biggest numbers at the right. And B-tree is a balanced tree, not a binary tree. So searching, insertion, and deletion is all log in as long as it remains balanced. The database will do that for you, so you don't need to worry about that. Balanced meaning from the root node, the top node, to the bottom node for all bottom nodes is the same amount of nodes to climb up. That means it's balanced. So say searching, I want to find value 999, which is at the bottom. So I start at the root node. 999 is greater than 800. so we go to 900. 999 is greater than 900, so we go to 999. Ta-da, found our value. Okay, so how does it work? Well, how does this actually work, right? So remember we had the cookbook, we went to index. So in database world, we went and found our value of 111, and what it had there essentially is, well, you can look at it as has a row ID. And that row ID is actually the database ID, and it goes to this row ID, it gets the 111, it gets this row ID, and then it actually goes back to the table and gets the rest of the information, which is a lot faster than sequentially scanning. And it's kind of like the cookbook. You don't have the whole recipe in the index, you just have, go to this page number and go find it. So, enough theory, right? It's kind of boring. Let's make this quite practical. Tell me what to index. Okay, let's do something really generic. Where or join, index it. Your primary keys, unique constraints will be automatically indexed. But like everything else in software, well, it's not that straightforward, obviously. So the point I'm going to hammer in today is know your queries. Know your queries are expensive or long running, the most executed queries and your most important queries. That will give you the starting ground when, where to create your indexes. So that comes kind of to the next point. Well, why not just index all the indexes, right? Why not just do absolutely everything? Well, there's trade-offs with indexes. Let's think the cookbook. We did a very simple one index on ingredient, but let's say I then do cuisine, I do category, I do maybe the chef, how long it takes, and your index is just going to keep going in size and keep going in size, and now your index is bigger than the book, so it became kind of useless. And you have to think, okay, there's also insertions. So let's imagine a book again. If I tell you, hey, here's a new recipe with garlic, and you go, okay, sure. You put that recipe in your book, you update your book with this recipe, and then you have to go to the index and update the index as well. So this is, if you have too many indexes, it's just going to get longer and longer and longer. In short, indexes give you increased read speed, decreased write speed. So now you might think, okay, well, why not? Okay, we know that we shouldn't index everything, but how do I know? I don't want to risk like having a poor performance. Your company's going to start losing money. It's not really nice to deploy something, sit there waiting anxiously, is it going to be okay or not? So again, know your queries. Do your queries need to be fast? And what are they for? So in our instance, they're for reports. Are reports time critical? Do they need to actually execute instantly? Generally, I'd say no. I mean, for the purposes of the talk, we want them, but in that case, no. Do you have a read replica, maybe, like a database that can bear the extra load of reading? Well, then maybe you don't need them. Now, when it comes to, say, application, do you have observability and alerting on your application that can indicate poor performance? Do you have a way to deploy this feature to a small subset of customers first and see what's going on before making a call to deploy to everyone? If you have something like that, then you can hold off on pre-indexing. But again, it comes down to knowing your queries, how much data is there. Alrighty, so more work time, which means more indexes to create. But there's a few caveats here. So first thing you might have noticed, dev was okay, but prod wasn't. And there's quite a few factors that come to affect this sort of thing. First of all, is the hardware that your database is running on is going to influence your results. The volume of data, so generally you're going to have a smaller set of data locally or in dev compared to prod. And the distribution of data is also extremely important as well. So that is something to keep in mind when you have indexes in different environments and stuff like that. And even some of these results today you'll see a bit skewed because I've just put this data on my machine. Okay, so first thing I want to cover is creating indexes the correct way. So I showed you this, but you're never going to do this because this locks the database against writes to that table, which in production, at least in my experience, that's usually, well, not very good. So we add it concurrently, and what this does is does a scan of the table and doesn't lock it, gets everything, and it kind of does it again afterwards to capture all the missing transactions from before. It's very high level, it gets a bit more complicated than that, but that's the gist of it. And there are queries that you can actually run to see is your index still being created or not. It's long and it's ugly, Google it if you want it, but that's the gist of it. Okay, before we do some work, we also have to talk about debugging. So The cool thing with databases is you can go to it and say, hey, what do you think you're going to do? And then you can also tell, hey, what are you going to do? What did you actually do? And then you can compare them and make judgment calls on that. So in Postgres, we prefix our query with explain. And that's essentially telling Postgres, hey, what do you think you're going to do here? Now you might be thinking, okay, how does it know what it thinks it's going to do? This is a very complicated topic, and bluntly put, this is a talk on its own. I went on a bit of a rabbit hole in this, and it's absolutely incredible how it does it. It uses all sorts of statistics and it's stored in the table to make these calls. So let's look at what this kind of looks like. So at the top, we have, you can see here, cost. That first number is the cost to find the first node, first row. Then the next number, which is 13,000 something, 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 that's the cost to find all rows, or what it estimates to be. The funny part about this, and this is a quote from the Postgres documentation, you might be thinking, okay, what does that number represent? It's an arbitrary unit. So it differs on your laptop and a bunch of things. There is a long formula. It uses like the hardware of your laptop, or your computer, all sorts of stuff to try and figure it out. So it's not particularly useful, you could say. Then we have how many rows it thinks match this condition, and the width of each row, which is in bytes, if I remember correctly. And then we could see it did a parallel sequential scan, which is what we talked about before, which isn't good. And it's going to do that twice, because 4 times 2 is roughly that. And then a filter. Then with the index scan, it's kind of similar, nothing too different. But the important part here, we can see it says index scan. So, well, let's do something a bit more interesting here. Let's see what it actually does. Okay, so now we're prefixed to explain analyze. Analyze will tell it, hey, can you run the query too, please? So we can compare. And what you can see here is after, say on the top line, after the gather, we have another one which says actual time. That's in milliseconds. So that's the time it takes to find the first row that matches the condition, and the time to find all rows that match a condition. And then we have a parallel sequential scan, how long it took. And then we can see here is rows removed by filter. That's the interesting part here. 2 lines above says loops 3, so that's times 3. That filtered out the vast majority of the table. So we generally say that's an absolute ideal candidate for an index when we see something like this. And this took 33 milliseconds. Now, let's see how fast an index is. Whoops. It was 11.8 milliseconds, so that was a third of the time of the sequential scan. And we can see it says index scan as before, we have all the stuff as well, index condition, but I just want to highlight the time that it took and how much faster it was. Okay, so now we've done a little bit of very, very high level of the query planner. Let's do some more work and let's see if we can learn more about this. So now product has asked us, hey, we don't just want author ID, we also want source ID, which is where we're getting that, because we're aggregated, we're getting these recipes from different sources and stuff like that. So our query is going to be something like so. Okay, cool. You can see here, we did this with no index, and we can see 27 milliseconds. And obviously it's going to filter a lot more rows this time. There's only 12 rows that match a condition, which is right at the top to the right. Cool, alrighty. So we create an index, and you can see here it's a multi-column index. The order that you specify the columns here is extremely important, and I'm going to explain a little bit more, but let's first see how fast this is. So from 27 milliseconds to 0.2 milliseconds. That is lightning fast. That is a pretty huge change, so that's quite nice, right? Let's talk about how I said the order. So we said multi-column index first. Second, I said indexes are ordered. So what does that mean? Well, if I create an index on author ID then source ID, what it kind of looks like is if I go to 111, let's use the cookbook example. I go to the ID of 1111, I find it, then inside of it, it's all going to be ordered by the source ID. Okay, cool. What does this mean practically? Okay, so we created this multi-column index, and if I want to query on author ID, source ID, it works fine, because I can go to 111, and within that I have 40, right? If I want to do just on author ID, that's going to work too, because, well, it's ordered first by author ID, right? But if I write a query and it's like, hey, can you get it by just source ID? Well, no, that's not going to work, because think of the book. It's ordered by author ID, so you have 111, you have a bunch of other IDs there. Within it, the source IDs. If I want to find 40, I'm going to have to scan every single author and find 40. At that point, the index is useless. You might as well just do a sequential scan. Cool. So what are the other options? Databases are cool. You can create 2 single column indexes and it will combine them for you automatically, which is pretty incredible. Okay. I've skipped something here. Selectivity and cardinality are 2 concepts in indexes that are extremely important. So what are they? Selectivity is given a value for, that you're searching for, how many rows does it return as a proportion of the table? Something like recipe ID, which is the primary key, so it's unique, is going to have a very high selectivity because realistically there's going to be 1 row with it. Then you have cardinality, and cardinality is given a value, given a column, how many possible values are there for a column? So maybe for something like source ID, that's going to be a low cardinality if we have maybe 10 sources that we always get. Something like recipe ID, author ID, will have a very high cardinality because there's a lot of possible values. Well, okay, why is this important? Essentially, forgive my absolutely beautiful diagram, but when you search on something like source ID, let's imagine that source ID returns roughly half of the table. Okay, remember I said it's a 2-step process here. You go to the index, from the index, you get the rest of the information. If I'm going to be going through, if I'm getting half the values, that's half the index or half the table. Well, what's the point of going to the index? That's just going to be slower. I might as well just go directly to the table, and that's what a database will do. The rule of thumb generally is if you're returning more than 10 to 15% of your table, your index is not going to be any good. Okay, know your queries. So what does this mean? We've had the multi-column index, which is quite fast, we saw. We can combine the indexes, but we can't actually, because source ID, an index on source ID is kind of useless. It's pointless. It's not selective enough. Okay, so this is where we think, what are our queries? Okay, so author ID and source ID. How often are we going to be querying author ID and then something else? We talk to product, we look at our code, and we see, we do it quite a bit actually. We do author ID and num ratings and quite a few bunch of others. So we can't just create a whole bunch of multi-column indexes because that's pretty inefficient, right? That's kind of a waste essentially. Well, there's a decent middle ground here, which is just create an index on author ID, and that will be flexible, it will serve all your queries, and it's going to be relatively fast. It's still going to be 0.9 milliseconds versus 0.2. Keeping in mind, without the index at all, it was 28 milliseconds. So that's still really fast, essentially. And what you can see here, what it does is we go to our book, I go to author ID 111, I grab all the values there, and then I filter all the values out that don't meet the source ID of 40. Cool, all right. So, more work. We want popular recipes for an author. Okay, kind of similar to before. We say author ID equals this, and num ratings greater than 5,000. Okay, it's a little bit different. Now, instead of 2 qualities, we have a range query. I've created this index here. It's actually wrong. I'm going to explain a little bit why it's wrong, but it's also very deceptive and it can catch you out quite easily. In this case, this will use the index. It's in 2.8 milliseconds, which is pretty reasonable. And you think, okay, that's good, but if I create this in the correct order, which is the columns are now the other way, it was half the time. You can imagine if this scales out, this is only 1 million rows, it's just, I haven't really fully randomly distributed the data, that sort of stuff. This can scale very quickly and becomes extremely, it can become an issue that you will not spot easily. You think, if it's using the index, why isn't it doing it? So the way to think about this is you want to reduce the amount of the index to scan. So on the left, we have the incorrect index. And what it does is, if you remember from before, it will go, first it's going to go num ratings greater than 5,000. it turns out when you do that, it scans a decent amount of the index. Whereas if I run the correct index, which is author ID 111, and it's quite a selective one as we saw before, it was only 1,000 rows of the whole table, well, that's not much of the index it has to scan. So that's going to be much more efficient. If you think of the cookbook, if I give you number ratings greater than 5,000, go to the book, okay, number ratings, okay, 5,000, okay, I've got to go, now I know everything after that is greater than 5,000. I have to scan all of that and figure out where the author ID is. Whereas if I go author ID 111, I find author ID 111, and all my values are there. It's a very small portion of the table we have to scan. It's going to be more efficient. So what to take from that? Index on equalities, then ranges. If you do that, you will avoid this issue biting you, essentially. If you're lucky, that query before the wrong one, it will just do a sequential scan. But if you can see that it can still use the index sometimes, and it won't be as efficient. Okay. Can we do this a bit better? What do I mean by that? Let's look at this query. First of all, we're selecting everything. Do we need everything? I talked to product, and product's like, no. We just want the recipe ID, please. That's good enough. Sure. Okay, so remember I said it's a two-step process, right? So I need to get all the values that fulfill this filter. Then I need to go to the heap or the table, the same thing essentially. Then I go to the table to get the rest of the row or what I've selected. What if I could tell our query or our index to say, hey, can you also chuck recipe ID in the index and don't go to the heap, and it'll be faster. So that's called a covering index. These are including Postgres 11 and onwards. Before you have to do a multi-column index, which isn't overly great, admittedly, but that's what it kind of looks like. And we can see here we've told it, hey, can you just put recipe ID with my index, please? And if you only select on recipe ID now, you can do an index scan. Well, actually, index only scan. And that's the important part to note here. It's saying index only scan. We see it took 1.09 seconds. It might not seem like a huge improvement here. It's because it's on my laptop. It's not a huge amount of data realistically, so it's still a 20% gain. This will scale very quickly. But one thing you might notice here is heap fetches. So heap is a table, right? Well, 0 here, but okay, why is that? Why is there a heap there? So essentially what happens is, this is a very high-level explanation, just for the record. It's a bit more complicated than this. When it goes to the index, it gets the value, and Postgres is like, hey, has this been updated recently? And if it turns out if it has to go to the heap and get this new value. So if you updated that row constantly, and you run this query, it will do a bunch of heap fetches, which is actually slower than an index scan. So that is something to keep in mind. Okay. What is the relation between time and rating for recipes with long cooking duration? So essentially, we're trying to look at recipes that take longer than a day, and we want to see the worst rated ones that have the longest duration. Something like so. Okay, cool. So what I mentioned before was indexes are ordered. So if you do what they call a forward scan, it's like ordering like this. Backward scan is ordering like this. What does that mean? Well, it means that we can avoid sorting when we do a query, which saves us a bit of time. Okay, so let's show. It's going to be a bit of a wall. Oh, that's all right. So you can see here we have a sort key, and now it's got all these values, and then it's run a sort on it. And that's taken 60 milliseconds. But if it was ordered already, it wouldn't have to do the sort, and it would come back faster. So first things first, let's create the index, which, of course, I've called it wrong because this won't quite work. Now it's down to 37 milliseconds, which is, I guess, a decent gain, but not a huge gain. And this is where it's a bit deceptive. I can see a sort method there, but I also see an index scan. Okay, but why? I've told it, like, it's ordered. Why can't you just give it back to me? Why do you have to do an extra step? Well, essentially, when you create an index, when I create it without this order here, it's going to create them descending and ascending. But databases can't scan the leading column in one order and the other column in another order. You have to explicitly define this to be able to do this. But it's worth noting this is an inflexible query. Now you have to use a query like this. Otherwise, you won't be using your index efficiently. Now we've gone down to 21 milliseconds, which is quite a decent improvement. That was half of the one before, which had the index scan but with sorting. This one doesn't. You can see here, index condition. You can't even see anything about the ordering. It just came back directly ordered, and it's a lot faster. Can we do this one better? Okay. Our index on cooking time was the first column that we specify when we created this index. Okay, let's visualize, as you can see, my beautiful visualization of cooking time. It turns out, we are also filtering on greater than or equal to 1440, which is minutes, that's a day, effectively. What does that mean? Well, if I was to represent the values of recipes that take more than a day, it'll be that little tiny black bar at the bottom. It turns out most recipes take less than a day. Kind of makes sense, right? Usually a recipe takes around an hour or less. Okay, again, know your queries. I talk to product, I look at my code, and it turns out that the only query we ever have to do with cooking time is checking if it takes more than a day. Okay, well, do we need to index everything here? What if we could just index what we need, which is recipes that take longer than a day? Cool. You can see we've essentially called what's called a partial index, and all we had to do was put a filter on it after creating the index, and that will do its work for us, the database. So when you use these partial indexes, you have to use the filter here, otherwise it won't use the index. So they are kind of inflexible in that regard. That's where you have to know your queries. And this time, admittedly, maybe the gains don't look as great. Again, it's my laptop, it's not a huge data set, but it's still around, I think, 4 milliseconds gain off the top of my head. So it's still a decent gain, and nothing really changes here. It just uses the index that's a lot smaller. So, partial index. What are they used for? We use it here to exclude irrelevant values. You can use it to exclude common values, so good examples are null. If you don't need null values, just exclude null values on your index. And another example that can come through is, we're doing reports, right? What if I had a timestamp column, and I talk to product, and product's like, actually, it turns out all our reports only need data from the last 3 months. That's generally how we do these sorts of things, right? We could exclude all columns that are more than 3 months old, have a timestamp that's older than 3 months, which would reduce the size of our index. And as I said before, it must use that filter defined in the index or not use the index at all. So, we need to fix some bugs. Product has came back to us and they've kind of been like, hey, the data's not quite matching up. We have some queries that filter on category. There's this experiment thing that's a tiny portion of the table, so it's very high selectivity. Okay, no worries. I find one of the queries here, and it looks something like this. I figure out, it's the casing. The casing's not correct. Okay, no worries. Let's fix this easily. I put in this. I deploy it. It doesn't work. Okay. I think, well, the index is there. Why is it sequential scanning? I don't understand. It was there, right? Like, come on, what the hell? Okay, sure. What the database sees here is a magic black box. It doesn't know that that function is actually related to experiment at all. It can't figure that out. It doesn't have that information. So it has to go, okay, well, it doesn't fit the index. I am now just going to do a sequential scan. Sorry. Okay, cool. We can fix this. Of course we can. We create an index, an expression index, function index, whatever you want to call it, and we put the expression inside the index definition, and now we've done it, we deploy it. Works all right. Okay. Some things to consider here. Very expensive. What happens every time you write to the database that fits this index, or if you update a row, it will compute the result of that and store it in the index. So they're not very efficient whatsoever. In general, I have set indexes, increase read speed, decrease write speed, but these are even more heavy, so do be careful with them. Don't use them just because. And I've used here maybe a bit of a contrived example, but know your queries. So where this can bite you is ORMs. ORMs can easily bite you here. You might not even realize it's putting a lower on your query, and you think, what the hell, it's not using index, this is ridiculous. Then you look at the ORM's query like, oh, okay, I see why. Timestamped, any function, Postgres function, will have the same issue. So always keep that in mind. Okay. So we're kind of getting to the end of this now, and we've done a bunch of work. I've shown the kind of query planner, very high level. Obviously, it's one of those things that gets complicated extremely quick, and I was trying to keep this somewhat short without going too deep into some things. So let's think. Okay, why isn't your index being used? Well, simply, the database can't use the index, or if things using index is slower. What are the reasons? So I've covered a few reasons. The first two I haven't covered. So table is too small. Rule of thumb, if your table is 2 pages, page is 8 kilobytes, it will not use the index. The way to think about it is if I have my cookbook, it has 3 pages and a 1-page index. What's going to be faster? You just might as well go through a table, right? I mean, through the book, right? It's going to be faster than going through the index. The operator is another sneaky one. So this is something that's going to be dependent on your database. Documentation will tell you. Something off the top of my head would be I like is not supported by B trees and Postgres. So be wary of those sorts of things. And we've talked about these, which was query returning too many rows. Your index is not selective enough. It will not use the index. You're using your multi-column index incorrectly or even inefficiently. And then we have function indexes being used incorrectly. But honestly, your database knows best. Yes, there are edge cases. I haven't covered them here because they're quite technical and require quite an in-depth knowledge of everything. But with my journey with indexes, going from someone who didn't know anything about them at all to now, I kind of realized database is honestly kind of magic. It's an absolute miracle that these things work as well as they do without any issues. We stand on the shoulders of giants when it comes to these things, so do keep that in mind. Okay. So I kind of said some of these things I've gone surface level, gets a bit more complicated, which might sound a bit of a cop-out. I've included some stuff here. If you're like, I want to learn more, please give me more. So first thing will be multi-version concurrency control. That's how we update the same table times, how it keeps things updated. Vacuuming is kind of related to that. And then the last one, which is how does your database calculate the statistics and how does it use the statistics in query planning? And you can add to that understanding the query planner even deeper. That was a ridiculously high level overview of the query planner. It gets much, much, much more complicated, extremely quick. So where to look? Postgres documentation is actually incredible. It's very in-depth, maybe not the most prettiest thing to read, but it does the job. There's a really good site called User Index Luke. It's a guy that is a database wizard as far as I'm concerned. He explains absolutely everything in depth. There's an article on everything, and it's really worth giving it a read. And yeah, so what's the takeaways from this? Know your queries. Again, what are your most important queries, most executed queries? What are your expensive queries? With that knowledge, you should be able to judge what index you should create. What are the trade-offs of you creating the index on the choices that you've made from creating that index? And from then, it's going to be a bit easier. That's all for today. Thank you. I hope you enjoyed my talk.
Thanks, Boris, and thanks everyone for coming.
I'm happy to take questions.
Oh, cool. Okay.
I thought it'd be a bit longer.
Yeah, cool. Questions?
For the creating the index and using the concurrently
Yep.
keyword, is that only for when you're creating an index after you've created the table? Or
Yes, so
Yep.
you'll need to create the index after table. So you can't do a migration that creates table and creates index. It won't work. You have to do it afterwards.
Thanks, Boris. You said there was a slight hit. If you create an index, there's a increased write time
Yep.
in order to build that index. Do you know sort of what numbers around that? Are we talking milliseconds, seconds, minutes?
It's a very good question.
It depends.
I forgot to put a disclaimer. A lot of this stuff, it's hard to quantify because it just depends on a lot of variables. What's the machine your database is running on? How much data does it have? The distribution of the data. There's lots of factors that come into this. So I can't just give you a percentage because it just depends way too much, but it will make your write slower, and the more indexes you have on a table, it's going to get worse. Rule of thumb, I would kind of say if you see more than 5 indexes on a table, it's a bit smelly. That doesn't look right.
Thanks for the talk, really enjoyed it. I'm just going to ask if you have any maybe really real-life examples of how you've used queries and maybe some of the foot guns you've encountered?
Yeah, I do. We have a few, yeah. One example, we have I can't give you the numbers off the top of my head, unfortunately, but we have a few, or we have one that just would not run at all. The query just would not return, completely stopped our processes. So I think it was a 2 billion row table, and we chucked the index on it, and it runs, I think, in roughly a second now. And that was a simple index too, but yeah, there's been a few things that we've done.
Yeah, thanks. Oh, did I? I'm sorry.
Thank you so much. I have a question. It's slightly related to index. So it's to do with the Postgres-specific random page cost and sequential page. I think it was random page cost, and the other one I forgot.
Sequential, yeah.
Have you ever played with that?
Yep. I kind of avoided it, but not deliberately. I talked a bit with someone who's a database god in our company, and he gave me a bunch of advice. So random page cost is, well, the cost essentially using index because it's random. Rather than going through the table, you're kind of like randomly going to the table. These days, it used to be a bigger issue back in the day with the old hard drives. We have SSDs now. The recommendations from the Aurora guys, people at Amazon, is you reduce, default sequential page cost is 1, random is 4. So the people at Aurora actually recommend Aurora database for AWS. They actually recommend dropping your random page cost to 1.5 or 2, I believe, off the top of my head, because we don't have hard drives that seek on a needle. We have SSDs, which are ridiculously faster, essentially.
Do you have any suggestions on how to safely test indexes in production? Or a system that needs to stay up?
Fingers crossed. No, that's a very hard one, and unfortunately, it's just one of the. So okay, there are some ways actually I can give you. If you have the same amount of data in dev as in prod, the distribution needs to be the same too. You'll actually get very similar results. Not timing-wise. There are other things you could do which get a bit complicated. Buffers is something to look at, which is the I/O work done. But even then, it gets even trickier because it's some things like if I'm running some of these queries again and again and again, you'll see the times change varying because caching, the database caching actually has caches in the operating system. So you can still use it as a judgment call if it will be performant or not. But what you could do if you really want, you create the, I don't know if your company allows this, but you can create your index, you can log onto the production database, create it manually, test your query manually, if you can bear the load and see if it will actually be efficient. That's one way I've seen of doing it if you're really not sure. But that comes down to just if you can deploy it to a small subset of customers and just see, hey, what's the impact here? Can we roll back quickly? That sort of stuff.
I just had a quick question about the specific data types that a database column could have. Would indexing affect that at any point, or should I say would the type affect indexing? So whether it be a date and time, would it be a JSON object?
Yeah. Do not create indexes on JSON. It's okay. I know we've tried to do it and it's not very efficient. There are other indexes you can use, but it's a bit hard to do from my understanding. Yes, the size of the value gets very important. This is at a very large scale. When you're talking like billions and billions of rows, that's when if you index on like an int, which is, I can't remember what the size is in Postgres versus the other ones, I can't remember, they're a bit smaller. You can see huge increases in times depending on that. And that's where you have to be careful. Covering indexes, like you don't want to put a JSON-B column in a covering index because that's going to make your index gigantic. What's the point?
Awesome, thank you.
Going, anyone else?
Cool. Thank you, everyone.
Thank you. So the next talk starts at 12:20.